Hi everyone, this is Mallika from Johns Hopkins University. Today I'll be talking about our work on how to accurately estimate total intracranial volume in magnetic resonance images using a multitask image-to-image translation network. A quick introduction on what and why we're focusing on the total intracranial volume or TIV. TIV is an important covariate that helps reduces variation in inter-subject head size and is also used in evaluation of various neurodegenerative diseases. So what is TIV? In simple words, one can say that TIV is the volume inside the cranium, and the cranium consists of the meninges and the brain. As you can see from the figure, the meninges consist of three thin membranes, that is the dura mater, the arachnoid, and the pia mater. In the image, we can also see that the dura mater is closely adhered to the skull surface. Since total intracranial volume is a normalization measure used to reduce variations in brain volumes, it is included in neuroimage analysis pipelines in the form of skull stripping tools. Most of these tools use MRI scans to approximate the intracranial volume by generating a mask. As you can see in the images, we've extracted masks from the Monster and BET algorithms. These masks have been superimposed onto the T1 weighted MR. However, it is difficult to estimate if the extracted mask encloses the entire cranial volume or not, since bone is not visible in conventional MR. We do know that CT is one such scan where bone is visible, so we've superimposed the mask onto the CT images. You can see that there are areas of under and overestimation of the volume. This leads us to believe it is important to estimate the dura or inner skull boundary in order to accurately estimate the volume enclosed inside the cranium. To summarize, we aim to estimate the skull boundary by synthesizing a CT that would improve the estimation of total intracranial volume mass given the input MR images. In this study, we use a T1 and T2 weighted MR image to generate the CT and TIV mask. In this study, we use a dataset comprising of 20 subjects from the radiation oncology department. Each data consisted of paired T1 and T2 MR with its corresponding CT image. All the scans have been registered to the MNI space. The scans have been super resolved and have an isotropic resolution of 0.8 millimeters. In this slide, we explain how our TIV masks have been annotated. We've used the available CT scans instead of the MR to develop a two-step delineation approach. An initial estimate of the volume is obtained using the active contour segmentation method, which was later manually corrected to remove any bleed-throughs. As you can see, we have highlighted a few areas of bleed-through, that is in the orbit region and the area where a portion of the skull cap is missing. These areas have been manually corrected to the image on the right. As we approach the base of the skull, we notice there's a lot of complex structures such as arteries, sinuses, foramen. We've made sure to use brain atlases to help us determine which areas are to be included. This is an example where we've included the internal carotid artery in our delineations. As we move further, we find ourselves approaching the lower bound of our delineations, which have been defined by the McRae's line. On the top right, we show you an animation of our 3D total intracranial volume that has been annotated by us. Hence, this completes our entire dataset where all 20 subjects now have a T1, T2, CT, and a TIV mask. Through this slide, we introduce the popular and well-established image-to-image translation network, that is Pix2Pix, which is also our baseline method. Now, Pix2Pix is a conditional GAN consisting of a generator and a discriminator pair, where the generator is tasked with generating realistically looking images, conditional on an input source image. On the other hand, the discriminator is provided with both the input source and the target source images, and it must classify the generated output as real or fake. The generator and the discriminator train in an adversarial fashion, that is, the generator tries to fool the discriminator. The network is trained using the objective loss function as shown, which consists of the adversarial loss and the L1 loss. The L1 loss term encourages the generator to produce images that is much more closer to the reality, that is, it's closer to the ground truth, by minimizing the pixel difference between the generated and the target image. As you can see, that pix-to-pix has been demonstrated on a range of tasks such as converting sketches to a product, converting satellite images to that of map images. It's also used to convert a black and white image to that of a color. We adapt the pix-to-pix conditional GAN network described in the previous slide to perform our two tasks, that is to synthesize a CT and to generate a TIV mask. Given an input X, in our case, we pass a channel concatenated T1 and T2 weighted MR image to the generator. The generator network then tries to output two images, that is, the CT and the mask. Each generated output is then passed to a separate discriminator head along with the source input and source target image. Here, the discriminators try to evaluate if the generated image is fake or real. In the next slide, we'll be expanding the generator architecture. The generator network used in this study is an encoder-decoder network with an unit-like architecture having skip connections in between the layers. But unlike the unit, this decoder branches into two different outputs representing our two tasks. The encoder, as shown, takes in an image X of the size 2 x 256 x 256, with 2 being the number of channels. In this case, we have inputted MR slices, that is T1 and T2 images, concatenated along the channel axis, and these go through 8 contracting blocks to compress the input. Now each block downsamples the spatial size by a factor of 2, so the output at the end of the encoder is of the size 512 x 1 x 1. Each contracting block consists of a convolution layer, a batch normalization layer, and a leaky ReLU activation function layer. The decoder, on the other hand, consists of 7 common expanding blocks, with 1 expanding block for each head to generate a different output image. The generated images are of the same size as the input but have a single channel. That is, they're of the size 1 x 256 x 256. At each expanding block, the feature maps are passed through a transpose convolution layer, a batch normalization layer, a ReLU activation function layer, before concatenating with the feature maps from the contracting block at the same level. We have added dropout to the first 3 expanding blocks. Prior to training, we set the accepted range of CT intensities in the range of -1000 to 1500 Hounsfield units, where air is represented by -1000 and the maximum bone intensities in all our CT is 1500 Hounsfield units. We have split our dataset of 20 subjects into 14 for training, 2 for validation, and 4 for testing. The scans have been normalized within the range of -1 to 1, and each scan consists of 241 slices. During the training, we applied data augmentation techniques such as random flipping and random rotation to the 2D slices. During testing, no data augmentation was applied. In this slide, we visually compare the generated CT to the source target CT. Given an input MR slice, that is, given the T1 and T2 slices, this is the generated CT and this is the target. We see that the generator could generate a realistically looking CT. In fact, in this case, the generated CT looks almost identical to the target CT. Now looking at a different set of MR slices, this is the synthesized CT and this is the target CT. We see that even though the generated CT resembles the target CT, there are some differences. That is, there are some differences near the sinus, near the frontal sinus, and there's also a difference near the cerebral artery. In the beginning of the presentation, we mentioned that it's important to estimate the inner layer of the skull to improve the generated volume mask. So we showed two cases pertaining to the top and to the base of the cranium. In the first case, we show you the top of the cranium. As you can see that this is the generated and this is the CT. And we see that the generated CT seems to be very close to the target, and the generator seems to have done a good job in producing the skull. However, on closer inspection, we find that the inner skull boundary is still blurry. We've also defined the lower boundary of our delineations to be the McRae's line. Hence, it's important to see how the generator synthesizes bones towards the base of the skull, given that there are a lot of complex microstructures present. This is the synthesized and the target CTs. You can see that the synthesized CT is missing a lot of microstructures, that is, it's missing a lot of bones. However, it can still synthesize the bones surrounding the lower bound of our annotations. We compared the synthesized CT generated by the network described in this work to that of the original Pix-to-Pix network using three evaluation metrics. The first one being the mean absolute error, which defines or which categorizes the average of the absolute difference between the generated and the ground truth image. In this case, we can see that our method could predict intensity values which were much more closer to the ground truth CT. We've also measured the similarity between the generated and the true CT using the structural similarity index measure. In this case, higher the value, better the result. Lastly, we also looked at the peak signal to noise ratio between the two images and found that our method did slightly better than the one generated by the Pix-to-Pix network. In this slide, we compare the masks generated from the described method and various skull stripping algorithms against the ground truth. The volume masks have been superimposed onto the target CT for better visualization. The mask extracted from the monster algorithm seems to have underestimated the volume in many areas as indicated by the arrows. When we look at the BET extracted mask, we find an area of overestimation. When we look at the Robex extracted mask, we find areas of over and underestimation. When we look at the HD-BET mask, we also see the similar case where the volume has been overestimated and underestimated in many cases as shown. Now looking at the generated mask, we find that visually this mask seems to be the closest to the ground truth. However, on closer inspection, we do see a missing area, that is, the carotid artery has been neglected by their algorithm. We also compare the volume masks generated from the network described to those obtained from skull stripping tools using performance measures such as the 95th percentile of Hausdorff distance, the dice coefficient, and the Jagat similarity. When we look at the 95th percentile of the Hausdorff distance, we find that we were able to generate a mask which has a difference of less than 2 millimeters. That is, it has a surface distance of less than 2 millimeters. And this is important since meninges are very thin and they can lie anywhere between 1 to 4 millimeters. When we look at the dice coefficient, that is the volumetric overlap between the results and the annotations, we find that our method is slightly better than other methods. Also, when we look at Jagat similarity, we find that our method actually did better than the others. Overall, we can say that our method could generate masks that is much more closer to the ground truth annotations. To summarize, through this study, we propose a way to estimate the total intracranial volume mass while synthesizing a CT from multimodal MR images. The architectural design of the CNN-based model allowed us to extend the well-established Pix-to-Pix network to generate two outputs simultaneously rather than using a series of cascaded networks to do so. This reduces the number of training parameters and also provides a better feature encoding. Although our method showed some improvements over the existing method, we hope to bring about more improvement by employing a 3D CNN instead of a 2D CNN. We also find that synthesis towards the base of the skull seems to be lacking. Hence, we aim on improving the synthesis of the skull. Working with a different set of cohorts should help us also address the issues with domain shift. This concludes our presentation. Thank you so much. Please do contact us if you have any questions.